This video is going to continue looking at the chemistry for carboxylic acid and its derivatives. Since the mechanism for this chapter is mostly the same, changing functional groups, I think it's important for you to recognize what are you starting with, and regardless of what your nucleophile is, what type of reaction is happening and what functional group are you getting. So without having to draw all the arrows here, you know if you have an acid chloride that you react with an alcohol, you're going to get an ester. You have an acid chloride with water, you're going to get a carboxylic acid. If you add an acid chloride with an amine, you're going to get an amide. So I think here, drawing them, you can't really prepare for what mechanism is going to be on an exam, but you can associate what products are without having to try to draw your arrows. Why do we need two equivalents for an amine? Well, after our first addition of amine has added to the acid chloride, we now have some acid running around as well as extra amine that can also act as a nucleophile to a later molecule. If that amine gets protonated, then you will have a protonated amine. It will not be able to be a nucleophile any longer. That's why two equivalents are needed. If you have a negatively charged nucleophile, I'm going to give you the template for what the mechanism would look like with an acid chloride. You would still have the same two arrows coming in, pushing out. You have your tetrahedral intermediate. At this point, you're deciding is the negative charge on the oxygen or the chlorine. You can push the electrons down to kick your chlorine out since it's the weaker base, and you get your ester. If you have a neutral nucleophile, you can use the same two arrows after you deprotonate, right? So since it's neutral, you'll need to make sure you're deprotonating before you go any further. The reason why is that the pKa of that oxygen is about -1 or -2. So it's going to lose that proton really quickly. After you've deprotonated your neutral nucleophile, you can then, same two arrows as last time, kick out your chlorine because it's a weaker base, and you get the same product. So your arrows really are similar except for your deprotonation step, and so I think it's more important you associate what you're starting with, what's your nucleophile, what functional group your product should be. Esters, same thing, right? We're going to be able to say what are our products going to be. So if we have acid with water, we can turn an ester into a carboxylic acid. If we have an ester with an alcohol, we can turn it into a different ester. And if we have an ester with an amine, we can turn that into an amide. Notice we don't need acid for the last reaction. The first step for these is, since acid is going to be present, you're going to protonate the oxygen of our carbonyl group. This allows for a couple different things. Once we've protonated this oxygen, and why do we protonate this oxygen versus the oxygen in our methyl group? We can look at resonance. So if we have resonance with that methoxy group, we'll actually have the negative charge on that oxygen, meaning there's a slightly more negative charge on our carbonyl oxygen than the oxygen in our methyl ester. Protonation actually does two things if we look at comparing the difference here. We now have a more electrophilic carbon, and we allow for a better leaving group. Two things, so a better electrophile and a better leaving group because we are having that protonation on that first step. How would this mechanism look? Our first step, since we're going to protonate, is going to involve taking the lone pairs of oxygen, going out and grabbing that hydrogen. At this point, we're now doing our same two errors from our nucleophilic acyl addition reactions, where we're adding water here, pushing electrons out onto the carbonyl oxygen. We now have a tetryl intermediate. If we had a neutral nucleophile, you would need to deprotonate before you go any further. At this point, notice we have an OH and an OH. Those are different OH groups from what we started with. But we can have either protonation on our OCH3, where we could turn into our carboxylic acid, Or we can have either OH group protonated, meaning we would actually go backwards, turning into our ester. Once our protonation on our methoxy group, we can now have a much better leaving group in which we would eliminate the weaker base. Electrons come down. At this point, we have a positive charge on our oxygen, so we would need a base to come and pick off that hydrogen. But we now have finished turning our ester into a carboxylic acid. You can also do the same mechanism in base, right? Here, since we don't have acid around, we can start with our traditional 2 arrows. We now have a negative charge on our oxygen. Our better base, or our weaker base, is going to leave, right? So our better base, meaning our oxygen, is going to push it down, kicking out our weak base. We then can deprotonate. Why do we need to do this step? If we have just kicked out a negative nucleophile, there's no way he's going to stay negative when we have an acidic hydrogen, right? Remember, that functional group right there is a carboxylic acid. So he's willing to donate that hydrogen. So you would have 2 pieces here, your anion as well as your protonated version of